So, today we are going to switch to the next topic, this heat exchangers. So, heat exchanger, I mean, as you have already seen, already three types you have seen. You have seen shell tube, you have seen double pipe, and you have seen plate heat exchangers. Why are they using different? So, you already experienced three different types. So, why do we need different types of heat exchangers? Why do we use shell and tube in any thought? It's okay if you don't know, we'll explain that today, but did you ponder about it? Okay, let's ask a simpler question. Why do we have double pipe heat exchanger in the lab? Why not shell and tube? What's the purpose of the lab experiment? You'll require heat transfer coefficient for all of them. See, this heat exchange which is happening between one fluid and another fluid, in all these types, there's no exception to that. And in all these types, the two fluids which is exchanging heat, they are not in contact with each other anyway, right? So, you have a tube, basically you have a wall in between, and the heat is transported from the fluid to the wall and from wall to the other fluid. So, that's common to all these three. So, why do we use different heat exchangers for different situations? Okay, so one possibility is surface area. Okay. Heat transported. So, efficiency. Okay. I could still use the same heat exchanger with similar inlet and outlet temperatures. So, what really matters is these two aspects, not just the temperature. So, efficiency can actually be looked at in two ways. One is the, I would say, heat transport efficiency. We will actually define mostly two lectures down the line how to define efficiency for these kinds of equipments and how do you use that aspect into designing the heat exchanger equipment. You also have to worry about the efficiency of momentum transport, which is where the pressure drop plays an important role. So, depending upon the nature of the fluid that you choose, as he rightly pointed out, depending upon the viscosity and other properties of the fluid, you will have to use different heat exchanger in order to maximize the benefit that you would get in terms of saving energy and also getting maximum heat transport. That is correct, because the pumping cost is going to be minimal. If you have high pressure drop, see, so if you want to pump a viscous fluid, you would never want to do it in a plate heat exchanger. Well, actually, I'll sketch how these plate heat exchangers and parallel plate heat exchangers, how they look like. And you also do not want to use a small tube diameter. You know, shell and tube, you have tubes which have a very small diameter. So, you will have a very serious issue in terms of transporting those fluid inside the tubes. So, design aspects comes into play as to which part of the heat exchanger you have to flow what kind of fluid. So, you cannot, so there is no specific reason, in fact there is no specific reason for your lab experiments as to why you should put monoethylene glycol in the inside tube and water in the outside. When there is one specific reason, the reason is that, which is not a very strong reason to do that, but particularly from the lab experiments point of view, the hot fluid is your monoethylene glycol, right. So, you are cooling the monoethylene glycol. So, if you now flow monoethylene glycol in the outer tube, then you also have to worry about the amount of heat that is lost to the surroundings. So, it is for that purpose that it has been made to flow inside. So, that has been worked out. Okay. So, pumping cost is actually very, very important when you design these kinds of heat exchangers. So, based on this, one can actually classify heat exchangers into two broad classifications. So, one is called the direct contact heat exchangers, and the other one is what is called as the transmural. So, all the heat exchangers that you have seen or sort of heard about, they are all primarily transmural. That is, there is no, in direct contact heat exchangers, we briefly alluded to this in the last lecture. So, in the case of direct contact condensation. So, direct contact heat exchanger is where the fluid is actually in contact with the other fluid directly. Transmural is where you have a solid which is present inside, like a metal for example, and that metal acts as a carrier for heat transport. So, in transmural heat exchangers, you need a carrier for heat transport. So, unlike in direct contact, you need a carrier for this particular case. Okay. So, of course, in direct contact you can have two possibilities. You can have direct contact condensation, which we already briefly explained yesterday, and you can have a direct contact vaporization. So, note that both of these, they involve phase change, and of course, you would expect that these two liquids should be immiscible, otherwise the purpose is lost. If the fluids are miscible, then it is no point in going for these kinds of heat transport processes. Okay. Now, in transmural, you can actually have two types. One, you have a situation where only single phase of both the fluids are involved, and one in which there is multiple phases. Okay. Multiple phases are involved. For example, it could be like a vapor stream and a liquid stream, or you can have a condensation process, or you can have a boiling process, etc. Okay. So, in single phase, you have three types. Okay. So, these three types is actually based on geometric classification. Okay. So, you have double pipe, and you can have compact, and you have shell and tube. Okay. So, typically when you have multiple phases, okay, so geometric classification, so this is geometric classification. These three are based on geometric classification, and in principle, even when you have multiple phases involved, you could use these three depending upon those three factors that we actually discussed a short while ago. Like, what are the important factors you have to consider while designing heat exchangers? So, remember that if you have multiple phases, let us say one of the phases, let us say condensing steam. Okay. So, it is a very common process where steam is now passed to the heat exchanger, and the steam condenses, and the latent heat is now used to heat another fluid. So, you have to be very careful as to which kind of heat exchangers you choose, because now you have to pump steam which is in vapor phase, and the density of steam is not as high as density of water. So, you have to take all that into account when you actually design and when you choose what kind of heat exchanger is used. Okay. So, now what we are going to see, so of course, multiple phases you will have going from liquid to gas phase or gas phase to liquid phase. Both these cases, and you have to decide which one to use. You would probably never use a double pipe when you have a liquid to gas or a gas to liquid when you have multiple phases, and we will see why that is the case in a short while. Okay. So, one can easily realize that heat exchangers are really the workhorse of many industries, not just chemical. So, you have it is a workhorse of chemical, of course, chemical industries, petrochemical, but in addition to that it has strong implication in pharma. In pharmaceutical companies, when you go, you will see a lot of these heat exchangers, because some of these drugs that they make, they are not always made at room temperature. They are all made in reactors. So really in pharmaceutical companies, it actually plays a very critical role, because the precision with which you want to make the drug is significantly high. You would never want to sacrifice on the precision of the composition of the drug. So the temperature of the material which is going into the reactor to get converted into the drug plays a very, very significant role. So heat exchangers and precise design of heat exchangers and efficient use of heat exchangers plays a very important role in pharma industries. They also play a strong role in biochemical industries. For example, some of you may not know, some of you may know how a vaccine is made. How many of you have had vaccination? I am sure everyone has had vaccination sometime or other in your life so far. So, vaccines are not direct chemicals. Some vaccines are attenuated microorganisms. Okay. So some vaccines, they are attenuated, typically using ultraviolet radiation, microorganisms, and some vaccines are actually generated in microorganisms. So the way the second one works is you use some of the microorganisms which can secrete some chemicals, some compounds it can secrete. So you tweak the organism, you cheat the organism, and you modify its makeup, and then you make it to produce large quantities of that particular vaccine. So this is done in, so these are called as, so you have biochemical reactors which can be used for producing some of these vaccines in a bulk quantity. So remember that when a vaccine comes into market, you really need like several lakhs and lakhs of vials, because there will be so many people who would want to get vaccinated. So generally for vaccination against virus, it is the first route that is used, and all the other vaccination typically it is the second route which is used. It is not always true, but typically. Okay. So here precise control of the biochemical reaction is extremely important in order to get good quality vaccine and also good quantity vaccine. So quantification is a strong function of the amount of vaccine that is produced in the reactor, is a strong function of the temperature at which the reactor is operated. You will see a lot more about temperature controlled reactions in your reaction engineering class, but it plays a very strong role here. So heat exchangers are used in order to heat some of these fluids, and therefore you can see that they are ubiquitously found in a lot of industries, which is useful. In fact, we do not know that heat exchanger is used in several of these places. We are going to see what are the properties of different heat exchangers, how they look like, what are their characteristics. Then we are going to look at how to quantify the heat exchange process. So, remember that the measurable quantities here are the inlet and the outlet temperatures and the flow rates, which is what all of you have measured in your lab experiments, double pipe experiments. You know what the flow rates are, you know what the inlet and the outlet temperatures are. So, based on this experimentally measurable information, can we quantify the extent of heat transport, and can we use that information to design heat exchanger for a given system. For example, it might be that I want to transport, let us say, X amount of heat transport rate. Okay, let us say the heat transport rate is Q. Okay. That is the amount of heat that I want to transport. What is the correct or the optimum design that I should choose, and what is the type of the heat exchanger that I should choose, and what should be the area of heat exchange, what should be the flow rate. So, those kinds of questions are actually very important in terms of handling heat transport. So, we are going to see how to design or obtain some of these parameters. We will not see all of them. You will see a lot more of these when you actually look at the process equipment design in your I think 7th or 8th semester, where all of these will be once again put together, and you will look at much more details about the mechanical design of heat exchanger. So, we will not look at the mechanical design, but we will primarily look at the area of heat transport, estimating the temperatures, inlet outlet temperatures depending upon the heat exchangers. Like you could have a question that, okay, here is my fluid which is entering the heat exchanger at a certain temperature, and here is the area of heat exchanger, and I want to know what should be the outlet temperature or what will be the outlet temperature. So, those kinds of questions we will try to answer in the next few lectures, and I will show you different methods that can be used for estimating these parameters. Okay. So, double pipe, all of you have seen, it is very simple. We just have two pipes. So, we have a double pipe heat exchanger, and you could have one fluid, let us say I call it fluid 1, which is flowing through the inside tube, and I could have another fluid, fluid 2, which is flowing through the outside tube. Okay. And the sub H, I use subscript H to refer to hot fluid and subscript C to refer to cold fluid. So, let us assume that the fluid which is going through the inside tube is the hot fluid, and the fluid which is going through the between the concentric circles is the concentric cylinders is the cold fluid. Okay. So, you expect that there is heat transport from inside to the outside. Okay. All right. So, now, so we could have a similar, so this is called the co-current operation, where both streams are actually flowing in the same direction, they are flowing parallel to each other. This is also sometimes called as parallel flow heat exchanger. Parallel flow and co-current flow, they all mean the same. Okay. Now, you also have another situation where it is called the counter flow, counter current flow, okay, where you have, let us say, fluid 1 which is flowing through the inside tube, and it is a hot fluid. Now, you have fluid 2 which is actually flowing counter currently to the first fluid. Okay. So, they are actually flowing counter current to each other. And there are some advantages with this kind of design, and we are going to see what those advantages are and why it is advantageous over the other one. So, one of your experiments in the lab is a parallel flow, if I am right, the other one is a counter flow. I do not know which one is parallel flow, laminar or turbulent? Okay. So, laminar flow is a parallel flow, and turbulent flow is a counter flow in your lab experiment. Okay. So, now, so let us look at the second one, which is the compact heat exchangers. A typical compact heat exchanger most of you probably would have seen in your, if you have a car or if you have noticed, you will see that the radiators that you have in the front, they are an excellent example of compact heat exchangers, okay, where you have the only difference there is that you don't have two fluids where heat exchange is happening. It's just one fluid which is carrying heat from inside to the outside. It's the air stream which is carrying from inside to the outside. But in compact heat exchangers in industries, what you can have is, you can have a situation where you have one fluid which is flowing through the pores of this array, okay, is going from one direction to the other direction, and you can have another fluid which is actually flowing through the other matrix, okay, and it's designed in such a way that they are not mixing with each other. Remember that it's, so you must remember that it's a three-dimensional array, okay, it's not a two-dimensional array. So you have a three-dimensional array, and then you make sure that the tubes are aligned in such a way, the slots are aligned in such a way that the fluids don't mix with each other, okay. It's like a monolith, okay. How many of you have seen a monolith? So this will be like a cascade of monolith where you will have, it's a three-dimensional object where you will have these slots which is going inside, and you can have two possibilities where you have simple parallel channels. You will have parallel channels, okay, where the fluid is, so I can probably try to sketch a top view of that. Okay. So you can have slots like this, okay. So if this is the top view, so you have one fluid which is going through these slots here. Now if I draw a side view, okay, you will have non-aligned slots like this, okay. So you can have another fluid. So this is the side view and this is the top view, okay. So you have one fluid which is flowing through these tubes, another fluid which is actually flowing to the other side, okay. And the reason why it is compact is you can have a situation where you arrange several of these slots, tiny ones, and pack them all together. So these kind of, and so one possibility is you can have parallel channels like this, or you can also have a cross flow channel, okay. You can have cross flow channel heat exchangers. So depending upon the properties of the fluid, the flow properties or the momentum transport, you can use compact heat exchange, different types of compact heat exchangers. For example, if you have a vapor stream, if you are exchanging heat between two gas streams or two vapor streams, then you really don't need that much pressure drop. You really don't need to pump it that much. So the amount of energy that you require to pump a vapor stream or a gas stream inside the compact heat exchanger is significantly less compared to that of pumping a fluid or a liquid through these tubes. So this is really ideally suited for heat exchange between gas streams, okay. And it is found in industry very commonly, it's found in industry. Okay, so that's the compact heat exchanger. This is the compact heat exchanger.